Yeah. So in the last class we have seen the uh, when we change the stator voltage, how the speed and torque of the induction motor was changing, and we have implemented this using voltage source inverter. Now today's class we will discuss that what is the effect of current source inverter, or what is the effect of stator current. It means when we change the stator current, how the speed and torque of the induction motor can be changed. Okay, that we will see. Okay, so before that, to understand the relationship between stator current and the speed and torque, we'll just bring this one equation here. So, before that equation, we will just draw the approximate equivalent circuit. So, equivalent circuit of the induction motor will draw. Okay, so this is X1, so R1 X1, R1 X1, R2 dash by S, X2 dash. This you know. And one more thing I will tell you that this current is I2 dash, whereas this current is I1. Here I1 is the stator current. This is the stator current. Current. So now you recall what is the equation for the torque production. This basic equation V by omega S, V by omega S, I2 dash square into R2 dash by S. This is your torque, electromagnetic torque produced in the induction motor. Now, this has a relationship with I2 dash, that is the rotor current. Now, one thing I will tell you that how can I find out I2 dash? I2 dash from this circuit diagram, I can find out something like this: I1 dash into uh, now there is a current division here at this point. There is a current division, so you apply the current division rule, then you will find out something JXM, because opposite impedance you will take. So divided by total impedance JXM plus R2 dash by S plus plus JX2 dash. So this you will find out. So I2 dash can be written in terms of so not I1 dash. I1 dash is not there at all. Only I1 is there. So I2 dash is equal to I1 into this. It means this I2 dash is proportional to I1. This we can say like this. So I2 dash is proportional to I1. How we got this equation? We got this equation using the current division rule. So I2 dash is proportional to I1. So the torque is proportional to, see, as the torque is proportional to I2 dash square, we can say this thing that torque is proportional to I1 square. It's a simple thing to understand. So torque has a relationship with I1. What is I1? I1 is the stator current. So this is the thing which I want to prove. Okay, so by changing the stator current, we can change the torque. So using this relationship, okay, I will draw some curve here. Okay, so what is that curve? Speed torque characteristics I will draw here. So we will see how we will get that. This is speed omega. This is the torque. Okay, then I will draw few graphs here. Okay, Okay, so this is for I1, this is for I2, and this is for I3. So for different values of currents, let me tell you, these are all are stator currents. Let me tell you one thing. For different values of the currents, stator currents, so how your torque is being changed. That is the point of discussion here. Okay, see this now. First we got a relationship, that there is a relationship between torque and the stator current. Then I have drawn the graph speed torque characteristics. Okay, we have drawn the speed torque characteristics for different values of stator current. So we got here I1, I2, I3, and the relationship between I1, I2, I3 is something like this. That what is the relationship here? You will find out is that I3 greater than I2 greater than I1. Okay. Uh, no, I think it's not. You just check yourself. As T is proportional to I1 square, so you will find out yourself is that if I increase I1, if I increase I1 for higher values of I1, for higher values of I1, everything remains constant. All the remaining things are constant. For higher values of I1, so definitely the torque is more. So I can say this thing that I1 greater than I2 greater than I3. Just check yourself. Okay. So increase the stator current, then the torque also increases. This is what we have seen for all the remaining values. Okay. Then we will have another plot like this. A similar kind of plot is there. Yeah. This is rotor frequency. Whereas this is the rotor frequency. So yeah, please see this here. We are drawing the graph between now. Okay, so one plot I have drawn between the stator current and the torque. Okay, and we will draw the relationship between stator current and the rotor frequency. So the graph will be something like this. Okay, so I will tell you how it. Now you have to change the S value. So you increase the value of S, then FR also increases. So here you see the rotor frequency and x-axis. So when you increase rotor frequency, it means what exactly you are increasing here? You are increasing slip. See, you are increasing the rotor frequency in the sense you are increasing the slip here. So when you increase the slip, so what will happen when you just see this equation? Remaining all these things you forget. Just see this equation. When you increase the slip here, this this S will be increased. If this S is increased, then this R2 dash by S will be decreased. It means the total denominator of this equation is decreasing. So if the denominator of this equation is decreasing, then what is IS value? IS value will increase. See here, once again I will tell you the relationship between rotor frequency and the stator current. We are drawing the graph now. So, for example, the rotor frequency increases from this direction, that is in the x-axis. So, when you increase the rotor frequency, it means you are increasing the slip. Why it is so? Because by having a constant stator frequency 50 Hz, you are increasing rotor frequency. It means you are increasing slip. Then only your rotor frequency will increase. So the slip increases. When the slip increases, you see the equation for the current here. So in the equation for the current, what do you find out in the equation for the current is that, please see here, your slip is there in the denominator. So when I increase S value, then this R2 dash by S will be decreased. It means the denominator is getting decreased. If the denominator is getting decreased, then the total numerator, that is IS, will increase. So that's the reason when I increase rotor frequency, the current also increases like this. Similarly, you can take the negative frequency also. It's just a image of that. You take the negative frequency also. Even though you take the negative frequency, then also the same thing, that you increase the negative frequency, then the denominator will decrease, so IS will increase. So 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 this is the relationship between stator current and the rotor frequency. This may be useful somewhere else. Okay, this may be useful somewhere. Okay. So now this is the relationship between stator current, okay, and how it affects the torque and speed. So we can conclude one thing, that what we can conclude is that by changing the stator current, we can control the induction motor, that is the speed and torque. That is the conclusion from this explanation. Okay. Now how do you change okay, how do you change the stator current? That's the question. Now how do you change the stator current is that, yeah. So we will take now just like how do you change the voltage there in case of the previous topics, that we use the voltage source inverter. Here, to get variable values of currents, we will use the current source inverter. Okay, current source inverter. So now I would like to right now I would like to tell you the operation of the single phase current source inverter. Then we can extend that to the three phase current source inverter. Okay. So now you see here, I will draw the circuit diagram of current source inverter. I hope you know the circuit diagram of the current source inverter by this time. Okay. So we just draw it here.
Sir,
Yeah, please.
sir, current source is nothing but a voltage source, no sir. అంటే whereas కరెంట్ సోర్స్లో అయితే మాత్రం కరెంట్ని కాన్స్టెంట్గా పెట్టుకుంటామా సార్?
Yeah, in current source, you will see voltage source inverter. What is the input voltage? It is a constant. Am I correct? VDC or VS or VD, whichever it is. Is it a constant or not?
Yes sir.
So here, what we do in the current source inverter is that you will maintain the input current constant.
Oh, okay sir.
So I will show you now how you can make this input current constant. How can you make this input current constant? Is that okay? So voltage source inverter. What is the difference between voltage source inverter and current source inverter? So one problem. Yeah, okay. I will do one thing. At the end of this current source inverter, I will tell you the differences between both the voltage source inverters and the current source inverter, so that we will know uh, that in which case which one you have to use. Okay. But right now, I will just clarify this doubt also. How you get the current source? How you get the current source? That also we will. Okay, so see here I will draw the circuit diagram. So from the circuit diagram, I will just show you uh, how you bring the current source inverter. Now I hope you know this thing. This is the source voltage, and this is a diode rectifier. So after the diode rectifier, you know very well that you will get the rectified waveform, something like this. Now after that, we will connect a large value of inductor. We will connect a large value of inductor. So what this large value of inductor does is now, see here. I hope you know the purpose of your inductor. Why you connect the inductor, and if the L value is large, then what is the nature of what is the nature what is the nature of its inductor? So if you have its very large value, then it will maintain its current almost constant. See the current source, practically they are not available to us. The sources which are coming to our home are the sources which are available in the laboratory. They are voltage sources only. But here we need a current source here. This is a current source inverter, so we need a current source. So how can you get a current source from a voltage source? That's what I'm just showing you here. How can I get a current source from a voltage source? Now this is a voltage source, AC voltage source. Then you have a bridge rectifier here. After that bridge rectifier, I hope you know you will get this waveform, full wave rectified waveform you will get now. So that waveform is passing through this inductor. So when it is passing through this inductor, now if you have this inductor current, if you have this inductance value very large, if you have this inductance value very large, then what is its nature is that the current which is flowing through this, the current which is flowing, for example, let me take this current as ID. The current which is flowing through this, it will be maintained constant. Why it is maintained constant is that's the nature of the inductor. You take the large version, but only condition here is that the inductance value should be very large. So now you see here your voltage source here, but at the end what you got here, a constant current or approximately constant current. So we can consider this entire circuit now, that is the source and the bridge rectifier and the inductor. We can consider this entire thing as a current source. So we can call this as a current source, this entire thing, because the nature of or the property of the current source is that it will have a constant current irrespective of the load. Whatever may be the load there, the current in that is constant, just like a voltage source. Okay, this is how you got the current source practically. And then now we will draw the current source inverter circuit diagram. So I just told you already that I would like to take the single phase inverter. Okay, single phase inverter, and I will extend this explanation. We can easily extend this explanation to three phase inverter. Then the L means load. Okay. Yeah, I will not give all the mathematical explanation here, but rather I will tell you the operation of this current source inverter. So can anyone answer that? Did you have this current source inverters in the power electronic course, or you did not have? Did anyone answer that? You have this?
No, sir.
You did not have this current source in your syllabus. You did not have.
It
I
is,
think
sir.
Yes, please tell. Okay, whatever may be the case, I will just explain you that. But few things you can easily the equations you can easily get that because some basic circuits you will get that basic circuits equations you might have got even in the voltage source inverter also. Okay, that I will tell you now. Now you see here now. So here in the current source inverter there is a load is here. So better we just fill the load so we will understand where is the load. Okay, this L is the load. L is the load here. So now you see. So we'll start the operation easily. Okay, so so before we start, see what is the logic here is that you have two thyristors T1, T2. You will turn on T1, T2 at some time. Then after that you will turn on T3, T4. See, this is very same like your voltage source inverter. Okay, you turn on T1, so T1, T2 will make a pair, whereas T3, T4 will make a pair. When T1, T2 are conducting, the current flow in the load is from left side to right side. Whereas when T3, T4 are conducting, the current flow in the load is from right side to left side. This is the difference you will find out. You can easily understand this difference. Then you have few things which you need to understand. What is this capacitor? What are these diodes? Okay, so I will give this capacitor as C1 and I will give this capacitor as C2. Okay, so few things are there which you need to understand here. Why we put this? Okay, why we put this diodes and why we put this capacitors, that also we will understand after the completion of this operation. Okay, but the basic thing is that you have four thyristors in a bridge, just like your single phase bridge inverter, voltage source inverter. So just like that, here also you have four switches. Two switches you turn on at a time. Then in that case the current will be positive. The other two switches when I turn on, the current will be negative. So positive current, negative current, positive current, negative current. So you will get different currents here. You will get different currents here. Okay, and okay. But anyhow, I will explain that for that first of all. So you see now carefully that how this operation. Okay, now you see. Yeah, we will start like this. We are going to turn on. Step I will take. Uh, to turn on to turn on T3. No, not T3. To turn on T1 and T2. That's what I am going to do now. Okay, I am going to turn on T1, T2. So so we will discuss the steady state case. Always remember, we will discuss the steady state case. So when I said steady state case in the sense, when I am going to turn on T1, T2 in the sense, before I do this, which thyristors are on? Before I do this, which thyristors are on is that T3 and T4 are on. See here, what I am going to do is that I am going to turn on T1, T2 now. But what is the status now? Initial status. We are discussing about the initial status because we are discussing the steady state case. When we discuss the steady state case, for every state you have a previous state. That's the steady state case. So here to turn on T1, T2, I'm going to turn on T1, T2. Okay, when I'm going to turn on T1, T2. Okay. So before that, what actually which switches are now turning on? Which switches are now conducting? T3, T4 are conducting now. T3, T4 are conducting now. And one more thing I will tell you that I will take a polarity of the capacitor as plus here. Because, and you will know, at the end of the cycle, you will know how comes the polarity here. This is plus, this is minus. So it has some capacitor voltage. This is plus and this is minus. So this is the initial status before I go to the step number one. What is the step number one? The step number one is that to turn on T1, T2. But before I go to this step, what is the present status is that T3, T4 are conducting, T3, T4 are conducting, and the capacitor C1, C2 have this polarity. This is the status. Okay. Okay. Now I will turn on T1, T2. Okay, so turn on T1 and T2. Please see here now. When I turn on T1, T2, what exactly will happen? Just see now. So when I turn on T1, T2, first thing is that so your T1 is on. So if your T1 is on, you see simple thing that T1, T3, C1. So let here T1, T3 and C1 makes a closed path. Makes a closed path. Why it makes a closed path? Because I said that you turn on T1. At that instant, we have seen this thing that T3 is on. T3 is on. So it makes a closed path. So when it makes a closed path, we will find out what is the voltage across T3. What is the voltage across T3? What is the voltage across T3? The voltage across T3 just because T1 is on, so it's a closed path, whereas this capacitor voltage is minus plus here. So you will understand yourself that the voltage across the voltage across T3 is negative. We don't write any value, but I will write negative. Check yourself. Just apply KVL in this closed path. Which closed path? T1, C1, T3. With this, it will take this closed path. This closed path. If you take this closed path, okay, so you will understand yourself that the voltage across T3 will become negative because you turn on T1. So when the voltage across T3 is negative, then I can say this thing that is that as soon as I turn on T1, T2, and when I take the case of T1, T3 is turned off. Not only T3, here also same thing. You take this closed path. Which closed path you will take here? This C2 is there. This C2 is there here. So as the C2 is here, okay, but there is a voltage across L is also there, but I will tell you what will happen here. Now, right now, we'll take an assumption. So what is L? L is the load. Okay. You recall yourself, just recall yourself that now it is an induction motor, say for example. It is an induction motor. Uh, or any motor you take. For example, any motor you take. What do you understand yourself when you take any kind of motor there? You know very well that it almost acts as inductive load. It almost acts as inductive load. Okay, so we'll do one thing. We'll approximate the load as inductor. See, it may not be exact inductor, but when we consider this as inductor and when we go to the explanation, when we see the situation, then after that, even though it is not exact inductor, but there is a deviation. That deviation will not affect the operation. That is the practically it is proved one. So we will consider L as inductor. So if we consider L as inductor, then I hope you know the nature of the inductor. What is the nature of the inductor? When I do the switch changes, okay, the inductor current remains constant instantaneously. The inductor current remains constant instantaneously. That's the nature of the inductor. So even though you have RL value also, but that R value is very small, okay, compared with L. Even though you take like this, the current in the load remains constant whenever you change the switches. Now, which switches you are changing here? You are turning on T1, T2. That's what exactly you are doing now. So you turn on T1, T2. So then what you find out is that the current will be remain constant in the inductor. So when the current is remaining constant in the inductor, you know very well the voltage across the inductor L di by dt is there. So your I is constant. So what is the derivative of a constant? Zero. So approximately the voltage across the inductor is zero. So just like it is acting as a short circuit. So if it is acting as a short circuit, okay. Now you turn on T2. Then what is the voltage across T4? What is the voltage across T4? So the voltage across T4 here also negative. Why? Because the capacitor has a negative terminal here, positive terminal here, and T2 you turned on. Your load is short circuited because you consider that as approximate inductor. So the inductor try to maintain the constant current. So if the current is constant in an inductor, the voltage across it is zero. That's the nature of the inductor. So it's a short circuit. Then you apply KVL. Then you will understand VT4 is also negative. So it means T3 and T4 both turned off. Why they are turned off? Because the voltage across them is now negative. So both are turned off. Okay, then what's next now? When both are turned off, what exactly happens now? When both are turned off. Okay. One more thing I will tell you that One more thing you must understand here is that, okay, so when T3, T4 are on, means before this step T3, T4 are on, what is the closed path? You must understand here. What is the closed path? The current is flowing. The closed path, the current is flowing. I will tell you here. I will write this step here. Uh, before this, before this first step. So before this first step, I said this thing that T3, T4 are on. So T3, T4 are on in the sense how they are conducting. That's the question. How they are conducting, I will show you here. T3, T3, then load, then T4, T4, and ID. I will say like this, something like this. I will show you here. See here. But I will take some other. So T3. You see the green color one. The green color one which I have shown, that the current will flow like this. So your ID will flow through this, then T3, T4, then through the load, then after that T4, D4, then after that it makes the closed path. So here see IDs which is here, it flows through T3, D3, then load, then T4, D4. So this is the closed path before I go to the first step. This you must understand. This is the closed path before I go to the first step. So what is the first step? You turn on T1, T2. That's the first step. But before that, what is the status? The status is that T3, D3, L, T4, D4, ID. This is the closed path it is making. So the green color path which I have shown, that is the path actually it is flowing. Now what you are going to do is that you turn on T1, T2. When you turn on T1, T2, what is the thing you observed right now? You observe that as the capacitor polarity is, this is minus, whereas the left side is minus, right side is positive. Here also left side is minus, right side is positive, and the current remains constant because of the nature of the inductor. So when we take these two into consideration, then you apply the closed path here, then you will know yourself that VT3, VT4 will be turned off because of the negative voltage across them. So here, how you are turning off the thyristors? Simple thing. How you are commutating the thyristors? You are commutating the thyristors when I turn on their complementary switches. Here T3, for T3, T1 is the complementary switch. For T2, T4 is the complementary switch. So as when I turn on T1, obviously you based upon this circuit arrangement, T3 will be turned off. Similarly, when I turn on T2, based upon this circuit arrangement, T4 will be turned off. Okay. Now we see what's next now. What's next is now is that, see here, okay, what will exactly happens now? Okay, you turn on T1. So I will do one thing. I will redraw the circuit diagram so that you will understand. So what is the status now? Please, I will just see this now. What is the status now? The status is that T1 and T2 are on. T1, T2 are on, and D3 and D4, D3, D4 are on. Why D3, D4 are on? You must understand this thing that why D3, D4 are on. Okay, what is the reason that they are turned on? I think I have drawn a wrong circuit. Okay, just change that. Okay, let's start with thyristors. Really sorry that I will change this. No problem. Just a small change. But that will not matter at all here. You don't need to worry about that. Okay, but both the cases that remain same. This, so just see what the mistake I did is that the mistake I have done in place of D2, I have done D2. Similarly here also. See, but that will not change the path. Let me tell you one thing. That will not change the path. So that remains same. So the right now, what is the status now? Before I go to the first step, that is turning on T1, T2. What is the closed path? This green color is the closed path. That is T3, D3 load and D4, T4. That is the closed path. Okay. Now what I did is that now I am turning on T1, T2. When I turn on T1, T2, by applying the closed path here and with the polarity of the capacitor which we know, we came to know ourselves is that T3, T4 will be turned off. So T3, T4 will be turned off because there is negative voltage across there. Okay. So now please see here now. What is the thing you will happen now? So what is the thing will happen is that, so I will just redraw the circuit here. We will not draw the entire circuit diagram. Just I will draw only. So see here, T1 is on. So I will put it as short circuit. Then I will write here T1. And T3 is off. Just now we have seen. So I will put it as open. And then capacitor is there. So I will just put the capacitor as it is. Plus, minus. Okay. And then D1. Okay. So now one more thing. D3 is on. You may worry why D3 is on. Because D3 must on. Why the D3 must on? Because so the current in the inductor. So then I will write directly here the load. Then after that load is there. So the load current is continuous. So to allow this current to happen, you don't have any other way other than conducting D3. You don't have any other way. You just see the closed path because the inductor will force the D4 to conduct. Sorry, the D3 to conduct, it will force. Then after that, what do you find out now? What do you find out after that is that I will write here D3, D4. See the inductor which present in the load here, L, it will force whichever the switches are there before and after, it will force them to conduct. Okay. So then it is D4. After D4, we have a capacitor. Then T2 is on. T2. This is T4. T4 are off. Just now we have seen. Yes. This is ID. Now this is the thing status. So here I will write myself once again that T and T2, T3 and D4 are on. Remaining all are off. Okay. See how comes these four are on? I will just tell you that I have triggered T1, T2. So no doubt in that. So T1, T2 are conducting. Now why D3, D4 are conducting? The reason why D3, D4 are conducting is that between D3, D4, you see here, where is the D3 here? D3 is here, D4 is here. Between D3, D4 you have the load. So when the current in the load has to conduct, when the current in the load has to be continuous, that inductor will force D3, D2, D4 to conduct. There is no other option left. So this is the closed path now. What is the closed path? See here now. ID is here, then T1, then after that through this capacitor, then through this diode, then through the load, then once again D4. Okay, I forget the polarity here. This is minus, this is plus, this is minus, this is plus. So now see the closed path now. I will write the closed path here now. What is the closed path? You will find out here is that T1, C1. Yeah, it is C1. It is C2. T1, C1, D3, L, T4, T2, T2, and then ID. ID is there. So that's it. This is the closed path direction. T1, C1, D3, L, D4, C2, and T2. Yes, this is the closed path. You will find out right now. Right now. So how we got this closed path? I will just repeat it once again so that you will understand. Okay, what is the closed path here is that, so earlier what is the status we have seen? The earlier status is this green color path which I have shown you, that ID flows through T3, D3 load and D4, T4. That's it. Now I turn on T1, T. When I turn on T1, T2, before when I turn on T1, T2, and the capacitor has already charged to like this with this polarity, left is minus, right is plus, and here also left is minus, right is plus. Then you apply KVL, then you will find out immediately T3 T4 will be turned off. So when T3 T4 are turned off, I have drawn the circuit diagram here. The equivalent circuit diagram I have done. T3 T4 are turned off. And then what is the closed path now? It is left now T1 C1 T3 L T4 C2 T2, that's it. So this is the closed path. Now one thing you will understand. What the thing you will understand here is that, okay, so this T1 you see here, this T1, okay. Now this current ID is flowing now through the capacitor. See here, now there is a capacitor here. I will just redraw the capacitor here. This is C1, so this is minus polarity, this is plus polarity. Now here comes your T1, okay, here comes your, I'm just drawing only that small part. Now how the current is flowing in this here, please see very careful that the current is flowing like this. So what does mean by the current is flowing in a capacitor when you have a negative polarity here, when you have positive polarity here? What does that mean? It means that the current which is flowing now, that is ID, the current which is flowing now, that is ID through the load, that is charging the capacitor C1 in the opposite direction, because the current is flowing, the current is entering the negative and it is leaving positive. So it means the capacitor has a charge with this polarity minus and plus, but you are forcing some current to flow through the capacitor in the opposite direction. It means here I can say this thing, that C1 is charging in opposite direction. See what is meant by charging in opposite direction? Charging in opposite direction in the sense negative charge here you have, whereas here you have positive charge. But you are charging in the opposite direction in the sense you are dumping positive charge in this plate, whereas you are dumping negative charge in this plate. So this is what happens. So when you do that, then at one instant, what do you expect? At one instant, the polarity of the capacitor here, this is minus, already plus, sir, this is plus, already there is a minus is there. So you are dumping plus and plus, you are more and more dumping plus, already some negative charge is there. Then what will happen? This negative polarity slowly decreases because it will neutralize with the positive polarity. So when it is slowly decreases, at one instant, both positive polarity and negative polarity become same, then the voltage across the capacitor now becomes zero voltage at one instant, I said. Okay, the simple thing to understand, there is a capacitor having one polarity. Now you send the current in the opposite direction, then obviously the capacitor will charge in the opposite direction. So it means, for example, this is minus 10 volts, say for example, then you send the current in this direction. What will happen is that this minus 10 becomes minus 9, okay, minus 6, minus 3. So likewise it go on decrease. So when it is going on decrease, at one instant it becomes 0 volts. Now that instant we will take now. So when I take that instant here, which instant? When the capacitor voltage is 0, then you will find out one very important thing. What is that thing you will find out is that, please see here. There is a diode is conducted here. There is a diode. Let's go to the circuit diagram. There is a diode D1 is here. So now this diode will be turned off when, as long as this negative is there for your anode. As long as there is negative, this diode will be turned off only. But now I said that this capacitor voltage, negative voltage goes on decrease, at one instant it becomes 0, I said. So it means what will happen is that the voltage across this capacitor becomes 0 volts. When the voltage across the capacitor becomes 0 volts, then this diode D1 will be forward bias. Okay, so I will write here, when the capacitor voltage it becomes 0, then D1 is forward bias. D1 is forward bias. The same explanation you can give here also. So the D2 which is here, is also forward bias. I will tell you what is the reason here why it is getting forward bias. Now because the capacitor voltage becomes 0. It was earlier minus volts, now it becomes 0 because you are forcing the current into the capacitor in the opposite direction. So the negative voltage decreases, at one instant it becomes 0. Once it becomes 0, ideally this D1 has no voltage, it means it has 0 volts. So okay, now what will happen after 0 volts to the capacitor? It will increase in the positive direction, that is plus 1 volt, plus 3 volts, plus 6 volts. Like this it will increase because you are still sending the current through that. So when you are still sending the current through that, this you will find out. So the diode D1, D2 will become forward bias. When they become forward bias, when the capacitor voltage C1, C2 becomes 0. Why the capacitor voltage are becoming 0 from the negative values? Because you are sending the current in the opposite direction. So now you see. So then what is the closure path now? If both are on, if both are on, which kind of closure path you will see now? Please see, I will redraw the circuit diagram. Both diodes are on. So if both diodes are on, then the new closure path will be something like this. This is E1. Okay. Then this is capacitor. It is short circuit. Okay. I will try capacitor. Capacitor C1. Okay. Then diode D1. Then diode D3. Now there is a load here. Then after that, T4 is already on, T2 is also on. Then you have another capacitor, T2, okay. Then T2. So the current is here and the current is here. So this is T2. Okay. Now you see yourself now. Now what will happen is that the current ID is here, the current is ID here, no doubt in this. Okay. What you find out is that, please see. Now I told you the capacitor now, so the current ID at this junction, the current ID at this junction, now will take two directions. One direction is this, one direction. This is direction number one, this is direction number two. It will take like this. Why it will take like this? Now this also becomes short circuited. This diode D1 which was present here, it is also, I will write here D1, D1, D2,
Sir,
D4. Yeah, please.
when diode D1 turns on, does diode D2 wouldn't turn off, sir? It reverse biases, no?
How it reverse biases here? Instead.
As polarities, previous it is positive, now it becomes negative, no, sir?
Which
Negative or
capacitor
it
you are
becomes
saying?
zero.
Capacitor you are
Both
saying?
capacitor.
Yeah, that's
We,
correct.
we,
So see, I have drawn the circuit. At which instant is that I have drawn the circuit that this is just become 0 volts. Okay. At that
yes, sir.
instant, I'm just explaining. You understand now? No, whatever is it is correct. I agree with that. But one thing I will tell you here. See this now. One thing what I will tell you. Just at that instant, what is happening? I'm explaining. No, after 0 volts, what it becomes now? It becomes positive. Positive in the sense what this polarity becomes plus, whereas left side becomes plus, right side becomes minus. So when left side becomes plus, right side becomes minus, immediately D2 should be turned on. That's correct. You understand what I'm saying? That's correct. But before this, before these things to happen, I am discussing that part. Which part now? Please see here. Which part it is that? Now you see at this instant 0 volts. So D1 is turned on, D2 is also turned on. Then the ID which is flowing here, the ID which is flowing here. Now this time it will get divided into two parts. One part is through the capacitor, the other part is through the T1. Am I correct or not? So this C1 will flow like this, then through D1. Then after that, okay. So then once again there is junction is there. Some current will flow like this, okay. Some current will flow like this. Then now by this time, what do you find out is that one important thing you will find out here, very important. So this is also ID. Then if it is also ID, then some part of the current is here, some part of the current here. Yes, so if you apply KCL in all the things, if you apply KCL in all the things, one important thing you will find out. What is the thing you will find out is that the current here becomes 0. Means the current gets reduced now. The current will definitely gets reduced. Okay, because the load here is there. So I told you already it will maintain the current. Instantaneously it will maintain the current. But after that, what will happen to the current? The current has to decrease. The current has to decrease. Immediately it will maintain the current here. But after that, the current will decrease. Now you see here, what you will see here is that the current here is get divided. Here also, the sum of these two currents is ID. So the current division will be there. So when you see this current division, when ID2 and ID3, this is ID2 and this is ID3, when both are same, you will find out there is no current in this inductor. There is no current in this inductor. Then what will happen is that one thing you will find out, one very important thing you will find out. Okay, that this current path, when you still charge here, then now we will go that this is plus, this is minus. Similarly, this is plus, this is minus. Okay. So the polarity gets reversed. So when the polarity gets reversed, so D2 will not conduct anymore now. That's correct. D2 will not only D2, even C1 also will not conduct anymore. Why it is so? Because D2 is turned off in the sense this becomes open. Now let me redraw the circuit once again. So here capacitor. Now D2 is turned off. Why D2 is turned off? Because this becomes plus, this becomes minus. Very simple reason why it is turned off. And then here D1 is conducting. Okay, this is T1, this is D1. Okay, then after that the current in the load gets reversed now. Current in the load gets reversed now. Okay. Then after that, what will happen now? What will happen after that? Then your DG is conducting. Now here also same thing. Capacitor polarity now plus minus. So if it is plus minus, let's see what is there here. Yeah, this diode D4. Now I will put here D2. So D4 is here. So D4 this cathode becomes positive. So D4 is turned off. D4 is turned off. And this is D3. Okay, and then after that you have D2. Now observe carefully what is the closed path now. What is the closed path? The closed path is now is that T1. This is ID. Then after that here, 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 here. That's it. So this is the closed path now. The closed. So this is the direction of the current now. So D2 will not see when D2 is turned off automatically there is no current in the capacitor. So when there is no current in the capacitor, the voltage across the capacitor remains there itself, whatever the voltage. We don't want to here discuss about the magnitude, but the polarity is important. So left side is plus, right side is minus. Here also same thing. When D4 is turned off, then the capacitor has no path connected. When the capacitor has no path connected, then its capacitor voltage C1. This is C1. This is C2. So both their voltages will remain constant because no charging, no discharging. Then what is the closed path now? The closed path is now T1, D1, L, D3, T2. That's it. This is the closed path. So now here now current is becoming negative. So first case, which case now? Before I start this operation, I have shown you the green color path. When I have shown you the green color path, you see yourself the direction of the current is from right side to left side. Whereas at the end of this operation, what I find out now, T1, D1, L, and T3, D3, T2. So the current gets reversed. See, it is now left side to right side. So if you take one current as positive, obviously the other current is negative. That's it. Okay. So now one thing I will tell you that. The waveform shape may not be as exactly as same like this. Okay. There is a small deviation may be there because of some reasons. But this is so positive current I and negative current. Positive current, negative current. Okay. So this is it. Yeah, please tell me, you understood now?
Yes, sir.
Okay, so your doubt is here that so T2 will be turned off. Okay, I also agree with that. That's the reason that I have redrawn the circuit here. T2 and D4 are turned off. So then when D2, D4 are turned off, C1, C2 also disconnected from the circuit. Then what is the only closed path left? T1, D1, L, and D3, T2. So the current in the load gets reversed. So positive current, negative current, positive current, negative current. So that's it. This is the operation of the single phase full bridge current source inverter.